Hi, it's product review time. We're going to take a look at the new Digilent Analog Discovery 3 because you've seen the Analog Discovery 2. It's incredibly popular, especially with schools and stuff like that. Could be, I don't know, I've been out of school for quite some time. So let me know, is this like the de facto standard in schools now? The software is killer for this thing, so it wouldn't surprise me. It has lots of popularity. It is cheaper if you're a student, by the way. This is the old Analog Discovery 2. This is National Instruments Edition. I don't think it's any different to the regular one, but Digilent have sent in the new Analog Discovery 3. Thank you very much. I've had this for quite a while now, but it was only released like 2 weeks ago or something, I believe. So we're going to check it out. It is... Oh, look at that. We get all stickers. Very nice. So we get some pin headers. We get a bunch of pin leads for it. And one of the big changes is it's USB-C now instead of USB micro USB. So there you go. There's our pinout diagram. And that's all she wrote. Oh, for those sticker aficionados. Oh, look at that. Like I bought one. Beautiful. So, yeah, nice green case. Don't know if it comes in any more fruity colors, but yeah, USB-C now, 5-volt DC. They have removed the headphone jack, which apparently, like, you can get like an additional board to plug into it or something if you want the headphone interface. I guess they took that out for some reason. And it's just the same, exactly the same interface as before, except the labels are now on here instead of on top here. I like on top. They should have duplicated those on top, I think. Yeah, it's neither here nor there. On the bottom, it's got nice rubber baby buggy bumpers, so yeah, so that's an improvement. It really doesn't move around much, at least on an anti-static mat like that, whereas this one was significantly easier to move around. So it's bigger and more betterer. Now, if we actually go over and take a look, link these in, we can have a look. It is 379 Yankee bucks. Yes, it is pricey for what you get. I mean, like, it's basically just an FPGA and a big-ass 14-bit analog to digital converter and DAC. It's, you know, it's not $379 worth of hardware, but as you'll see, all the value of this is in, most of the value is in the software, the Waveforms software. So anyway, it is backward compatible, adjustable system clock now, whereas it was 100 megahertz before. So now you can adjust it from 50 to 125. That might be useful for some applications, for, you know, if you're matching sample rates or whatever. All instruments are available in every configuration, no more losing access to digital I/O. So it's basically got a bigger and better FPGA in it that allows you to do a lot of extra stuff at the same time, whereas before there were limitations. Now there's lots less limitations, or no limit. Don't know if I'm not going to say there's none, but anyway, USB-C. I don't think it gets you any faster throughput. I think it's just a USB-C interface. Is it? It's got the same 14-bit resolution differential analog to digital converter, 9 megahertz bandwidth, minus 3 dB point, 16-bit resolution, sampling a quarter of the system clock. Maximum sample buffer has doubled from 16 to 32K. That's part of the FPGA difference, and hardware fur filters for each input. So it's got hardware filters now instead of software inputs. We might be able to demonstrate that. That would be really cool. So you can feed your signal in there, it can do hardware filtering, and then you can output it straight to the DAC. That's it's pretty versatile stuff, and apparently you can sample it straight in, whereas before you had to, if you wanted to know what you were outputting, you had to use one of the channels to feed back or something like that. Anyway, two single-ended analog outputs, plus minus 5 volts, 14-bit resolution, exactly the same. They're doubled that. 16 digital IOs are all still the same. I think, though, they have removed the 1.8 volt LV CMOS though, but plus 5 volt, minus 5 volt power supplies are 2.4 watts each, but I think you have to use the external plug packy for that. And there's a very comprehensive article here written by James Colvin, who's one of the developers of all the apps and the reference things and whatnot. So they have actually reduced the price from $399 Yankee bucks to $379 bucks, and I won't go through, but they've basically upgraded from a Spartan 6 FPGA to a Spartan 7. Inside we'll open it up and we'll have a quick squeeze, but there's a whole ton of other stuff that you can do in this new one with the new FPGA that you couldn't do in the previous Spartan 6. So it's basically they've lowered the price a little bit, and yeah, it looks like it can do some really versatile stuff. Anyway, let's go back to the videotape. Let's take this apart. Now, while I'm taking these apart, let's talk about the price. 379 Yankee bucks, which seems crazy. I think it's about $250 if you're a student or something. Don't quote me on that. Anyway, there is a student discount for that thing. Now, for that sort of price, you can buy a proper 4-channel desktop scope. Like, you can get your Rygold. Don't know if you can get the Siglet that cheap, can you? But it's pretty close, right? It's basically the same price as a desktop scope. So why would you buy this sort of like dinky looking thing with no real like front end? You know, it's got no, like, doesn't have a proper front end in it. Why would you buy this instead of buying a real benchtop scope? Well, and it's only got like 9 meg bandwidth. This bandwidth isn't, you know, 150 meg, 100 meg or anything like that. Why would you buy that? Not only does it have a dual 14-bit ADC, it's also got the 14-bit DAC as well. So you can output signals, and as we'll see, all the value is in the software. This can do a ton of stuff you simply can't do on a benchtop scope. But it is no replacement. Like, you shouldn't even compare these two. You can't compare this to a benchtop scope. It's horses for courses. How do I get this bloody thing open? Proudly designed by Digilent Inc. in Romania and the United States of America. I think it's made in China, though. Secret squirrel screws under there. Unbelievable. All right. Oh, we're in. Look at this. Okay, that is significantly different, isn't it? Oh, look at that. We've got a big metal... Oh, here we go. There we go. We've got a big metal can over here. That's interesting. There you go. So there's the new Spartan 6 FPGA on an angle for routing... Spartan 7 FPGA for routing reasons, of course. And the previous one is over here. There you go. It went from a 6 SLX16 to a Spartan 7 XC7S25. So significant upgrade there. I'm not sure of the price difference, but they have actually lowered the price here. So anyway, looks like there's our DAC. We can call up the specs on that. And we've got a TI 3644. That'd be the 14-bit analog to digital converter there. They have been working on this for a while. Copyright 2022. Got some real overexposure issues there. Sorry, you can't see the... There we go. Let's turn the iris down a bit. And there we go. We've got 2 relays here on the input. They're trimmer caps there. For your input voltage divider. I think there's only 2 ranges on this thing from memory. And then we've got the input buffer, and it's a dual ADC. I think it's a dual ADC. We'll have a squeeze in. Yes, low power dual channel ADC. Then we've got our DACs on our output. And it looks like they've got the requisite grounds in here. Look at the vias and stuff. It looks like they did have... Look, they've thought about putting a metal can on here, but they didn't. So that's interesting. They've got a metal can up here. So I assume that's like the switching converter up there, but they didn't put cans on the analog front end or the ADC. So that's rather interesting. I guess, you know, the whole idea is you want to keep the crap from here out of here. So let's just put 1 can on here instead of having 3 cans. That's probably easier. It's not much else. There's an FTDI chip here. Then we've got, like, is that a 1.6 volt voltage regulator? Is that a 1.0 volt voltage regulator? That'd be for the FPGA cores, would it? So... Yep, some switching converter here. You can tell by the inductors. You don't even have to look at the chip number. And yeah, not a huge amount more. Not too fussed about that. So there you have it. And under the can... Oh, I thought that can would prise off. It doesn't. It looks like it's soldered down. Yeah, I couldn't be bothered getting that off now. I'm not that fussed. That'll be the DC. That'll be the power supply section there, I would presume. And for those curious to see the other side, yes, it is a double-sided load. They couldn't fit it all on the top, even with the bigger board, so that'll cost them a bit extra. A little bit extra, of course, to make that. So that'd be, is that your protection for your logic analyzer? Yeah, that looks like protection for your logic analyzer there. No wuckers. Yeah, so there you have it. There's the two of those. Was that yeah, that was a significant double-sided load. So yep, that is more betterer for less cost. Has anyone actually costed out? Well, this one's so new, maybe someone hasn't done it yet. Has anyone actually costed out the Analog Discovery 2 or the 3 for that matter? It'd be interesting to know what the BOM cost of this thing would be in volume, but they're making a crap ton of these, so yeah, the volume's huge. So there you have it. That's a 14-bit 125 meg sample per second low noise dual pattern channel ADC, blah 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 blah. And our DAC is this jobby here, and it does have an amplifier to give I think plus minus 5 volts output, which is quite reasonable. Oh, there's a little light pipe there. Where did that fall out from? I don't see a hole in the case for it to pop out there. Is it at the side? It's got to be the side somewhere. Oh yeah, look at that. Isn't that cute? Just fits in there like a OJ glove. And for those wondering what that does, well, here's our LED down here, and it's a vertical emitter, of course. The light's coming out the top of the board, and how do you get that out the side? Well, they could have just used a right angle LED, but you know, nastier or whatever, like especially like a surface mount version like that. So you just use a light pipe and it just takes the vertical and bends it a bit, and it comes out the front of the case. No wuckers. But that's another part you've got to add to your bill of materials, then you've got to engineer it and have it manufactured and everything else. So, you know, adds to the cost. I do like how they added a slot to the board down there, and that just holds that light pipe in place. That's very nice. Yeah, hats off. More attention to detail. The rubber feet here, they've done a curved slot there, and that just goes in like that. So there's no way that can come off. It's not just stuck on. They've actually, you know, put a bit of pride in the design of this thing. Nice. And because the pinout is exactly the same, I can reuse the breakout board that I've got for the two waveforms and the channel 1 and channel 2. Doesn't add any extra ability. I mean, it does have like AC-DC coupling, and this has a 50 ohm output termination. But apart from that, doesn't add any like extra vertical attenuation on the front end. You're still limited to the two ranges of plus minus 2.5 volts to plus minus 25 volt input ranges on this thing. And I think the waveforms are only single plus minus 5 volts out. But anyway, with the 14-bit converter, it's still pretty schmick. Anyway, download the latest Waveforms software. Did have to register to get to the download page though. That sucks. Come on, seriously? Anyway, we've got scope, wavegen, power supplies, voltmeter, and the power supplies can actually be modulated, apparently, like slowly modulated. They're not like the arbitrary waveform generators, but apparently you can slowly modulate, so you can do like ramp ups and ramp downs and stuff like that. Great. We'll actually see if that's the case. And then you've got a voltmeter, you've got a data logger as well, logic analyzer, pattern generator, static I/O type stuff. You know, if you just want to light up some 7-segment, I think that's the example, 7-segment display there. They've got a spectrum analyzer, a network analyzer, and they've got an impedance analyzer as well. Fantastic. And they've got a curve tracer. I didn't know, I've never played with that before. Protocol analyzer, which what sort of protocols do you get? UART, SPI, I2C, CAN, CEC, JTAG, SWD, and AVR as well. Nice. And then you can do custom scripting as well. I've never tried to script this thing, so I don't know, but apparently it's really good. And apparently it integrates with MATLAB, and because National Instruments own it now, I think it integrates with National Instruments tools somehow and all that sort of jazz. So automation is pretty high on the list here. Anyway, so we can go to, if you just want to get back, you can get to welcome, so we can go to any of the, oh, I just heard the relays click down in there. And we're good to go. Like, it just automatically detected it down here. And can we call that up? Yep, there you go. And then we can set all the stuff internally. Now, I didn't know about this. Can the Waveforms software actually support your sound card? Really? That's fantastic. Can you just download this for free? You got to register, but download it for free. And can you turn your sound card into an oscilloscope? I didn't know that. I might have to try that on the, I just do like a quick second channel video and try that out, actually, if that's the case. Wow. And I don't know what these other products are, the E-Explorer, the Eclipse, the Digital Discovery I've got, that's a different product, Discovery Studio, I'm not sure what that is, but there's, yeah, they've got all these different ADP, I don't know. So, but yeah, anyway, we've got the Analog Discovery 3. So you can see the difference in the waveform memories and stuff here between the 3 and the 2. There you go. They are much smaller. So yeah, this had, apparently they have removed the 1.8 8 volt digital input here. That's just, yeah, that's Gonski. So these are the different modes that you can actually configure. You can only select like one of these modes. So Discovery 3. So you gotta pick your poison here. What do you want? And why would you want to select like a lower memory range, like 2x4K, for example? Because it faster updating, more better updating speed. So it's a trade-off between, I presume, your updating rate and your memory depth. But that's typical of these types of scopes, which do the capture and then dump the data. Capture, dump the data, capture, dump the data. I don't know what settings we're at, but I'm just running this now. And as you can see, we're taking 16K samples at 1.58 meg, and that's kind of the update rate. So can we change this in real time? No, it stops updating when we do that. That's a bit of a shame, isn't it? Anyway, let's go to the 2 channel by 4K option, shall we, for the scope. So if we select that, no, that looks like a similar, is that a similar update rate? 4096 4K at 400 kilohertz now, so they can't run it at the same clock rate they could before for a given time-based setting. Move my head out of the way here, and this is how we control the input here. So we can turn off channel 2. If we want, turn off channel 1 or channel 2, and we can set offsets here. The controls are what you expect for a USB scope. They're not, you know, absolutely terrific, but they do the job. So we have a selection between 5 volts per division like this, but really I do believe these are only fixed to input ranges physically on the front end. So, but they're doing that. You know, they're giving you the traditional 125 sequence to make it a familiar scope interface. That's nice. And there you go. If we switch to 5 millivolts per division, you can see, well, we can stop that. Okay, you can see that, yeah, it's software magnified like this because we don't have a true 5 millivolt per division. I believe it's like, it's just 2.5 volts. Like input plus minus 2.5 volt input range, but you've got to divide that by 14 bits. Let's get the confuser out here. So we've got a 5 volt range plus minus 2.5 volts divided by 2 to the power of 14, 16,384. That gives us 305 microvolts per bit. So, you know, it's not too shabby. So we can actually go down to 200 microvolts per division like this. And you can see, let's run that again. It's hard to sort of see, but each one is, yeah, around about that 300 microvolt level there. So, you know, that's a bit how you're doing, 200 microvolts. I don't even know why they bother. Like 1 millivolt is fine. It's just, you know, marketing wankery, really. Anyway, let's go into the wave gen. Let's see what we've got here. DC, sine, square, triangle, ramps, noise, pulse, trapezium, sine, power, see, scope, channel 1. Okay, so you can take it from the, I don't know what C sharp is there, but scope channel 1, it looks like you can take it from the ADC. So it looks like that's looping the channel 1 ADC back to the DAC output. So that's pretty darn flexible. And then you can filter from channel 1, right? So we can take an input signal from channel 1, filter it, and then output it on the arbitrary wave gen. Nice. And that's done in, I believe that's done in the hardware. As I said, hardware filter, it's done inside the FPGA. All right, I've enabled both channels here. So what I'm going to do is feed and generate a signal on the output of channel 1. So I'm going to feed up its own clacker here. I'm generating a waveform on waveform channel 1 here. I'm going to feed that into channel 1 ADC, the scope input, and then we're going to filter that, and then we're going to output that on waveform channel 2, and then read it back on channel 2 of the scope. Let's see if we can do that. I don't know. I haven't tried it yet, but I think we can. So if we go into channel 2 of our arbitrary waveform generator and we select the source for that signal as the scope channel 1, which we're reading in, okay, from the ADC, we can actually read that in. And if we do, let's just do 50%, okay? So it should actually, well, no, we'll do 100% first, okay? So we'll go over here and we'll see that they're actually, there's 2 waveforms there, right? There's channel 1, channel 2 is identical, because channel 2 is being fed from waveform generator 2, which is being fed from analog ADC input channel 1, which is being fed from the arbitrary waveform generator. This is amazing. Like, I can just think of, like, I can remember when I was studying how useful this would have been, like, from in an educational scenario. If I was teaching stuff, oh my goodness. Like, just the flexibility, just with the 2 channels here, the flexibility you can do with this sort of thing is absolutely amazing. Anyway, right, so we can do this all in real time. So as I said, we can set this to like 50%, and now our waveform Gen 2 will be 50% of what we sample in with channel 1. So it should automatically be half. Yeah, there it is, half, right? It's half the amplitude. Nice. And we can offset that by a volt if we want, right? So let's do that, right? So it's 50% of the amplitude plus a volt up. And is that what we see? Oh, we don't. Why? No? Oh, are we AC coupling or something, are we? Oh, yeah, no, silly me. That's actually my hardware doing that. You will see I'm AC coupling. Okay, so let me go to DC coupling. And this board doesn't come with it, by the way. I had this for my Analog Discovery too. So, and bingo, there it is. You get your 1 volt offset. Nice. So can we actually filter stuff like this? Let's go back in here and let's experiment. Once again, I haven't read the manual with this, right? So look, we can get like an average. Is this like an average responding? Let's have it. Let's see if that makes any. It shouldn't make any difference. No, and it doesn't. Okay. So filter channel 1. I don't know what filter C4 is. What's C4? I'm going to have to RTFM on that. But can we go filter channel 1 and go, whoa, that's off the scale. Okay. So what is that filter doing? What's that C sharp or C hash? Yeah, I don't know what the C hash is. Like, is it being programmed in like C sharp or whatever? I don't know what the deal is. Can we actually sweep the channel coming from the ADC channel 1? I think we can. Check it out. We can damp it to 5%. Like, we can damp it to a percentage, right? In like a certain time period, like 100 microseconds. Wow, look at that. Look at that. And you'll notice the shaded part in here, it looks like we have a persistence display in there as well. That's a nice touch. So look at, like, just think about what's happening here. This is just nuts. Now you can actually move these vertical. You can just grab that with the mouse and just move it, as well as like using the offset thing over here as well. And if you want to select channel 1, you just go here and then we can just move channel 1 like that. But you'll notice that it is changing because we're actually offsetting channel 1, what we're reading in. So what we're reading in with channel 1 is impacting what we're generating on our second channel arbitrary waveform generator, and which then is being read by channel 2. Like, how good is this? This is just amazing. Wow. So unfortunately, I haven't figured out this filter yet. And I don't know why it's got filter C4. I don't know what C4 means. That like channel 4, there is no channel 4, right? So like filter channel 1, if we go there and then, run like that, okay, what's happening? Yeah, we've just got a massive signal there, so let's get rid of those and we filter. Yeah, I'm not sure what's going on there, right? Because all I'm doing, like, I'm filtering. I don't know what the filter's actually doing and where you set that up. Like, it's not in here. So once again, like, I haven't read the manual. This is like my first time playing around with this new Analog Discovery 3, and I haven't played with the original one for donkey's years. So yeah, please forgive me, but you can see like the amazing capabilities I've made this do in just minutes of just plugging it in. And as far as the help goes, look, it's all built in. So if we do, hopefully, if we do want to find out, actually, it'd be nice if I could like right click on that and like call up, you know, and say, I want help on that. Like, what is that? Like, what is that feature? It'd be nice if like that would, if there was a button next to everything that automatically hyperlinked you over to the various help. But, you know, I mean, it's fantastic as it is. But yeah, that just would have been a nice touch. But anyway, I wonder if it's in here. Oh, and it's got an editor for your arbitrary waveform shapes as well. Once again, like, I won't go in and play with that, but like, that's just like serious. Like, look, you can put tables of stuff in there. Oh, goodness. Oh, wow. Custom math functions and things like that, and just let it generate, as well as importing like existing things, and presumably like you can save the ADC and then you could import that, you know, you could modify it elsewhere and then you could bring it back in. But wow, just the like the customization of the arbitrary waveform generators combined with the ADCs. This is incredible. Now, unfortunately, the help doesn't tell you anything about those extra types. Like, yeah, it just doesn't tell you about these extra types here. So that's a little bit disappointing. But, you know, like I'll eventually figure that out, but just not for this video. And let's go to the power supply over here and see what we've got. Here we go, positive and negative supply. This would all be that stuff under the can in there that we saw. Got an internal temperature sensor. That's the die on the FPGA, so that's run at almost 64 degrees there, Fahrenheit for you Yanks. USB voltage 4.7. I'm just powering this from a USB 2, by the way. I'm not powering it from like a USB C or USB 3. So is that how much current it's actually is its own current consumption? So there's not much left over on that port. What is it, 1 amp port or something? So there's not much left over to power our product. So that's why it has an external 5-volt jack on it. So then you can actually supply the more output voltage there. But anyway, positive supply. Oh, it looks like it's already on. There you go. So we can just use that bar, or can we type in? You betcha. Or we can set maximums too, so that we don't accidentally, you know, damage our circuitry. If you've got, you know, a 3-volt circuitry, you don't want to accidentally, you know, slide that bar all the way with LBJ right over to 5 volts and then blow up your bloody, you know, your expensive widget. So yeah, that's pretty cool. Oh, and we can have a track-in power supply too. Nice. Muster enable is off. How about we turn muster enable on? There we go. Hardware power limit, okay, and then we can set a power limit as well. So you can go up to 15 watts here. Wow, okay, yeah, but of course I don't know if you can do that from the USB-C. Supplies, Analog Discovery 3. See power supplies for more information. So yeah, it looks like it does have extensive fusing inside here. So you shouldn't be able to blow up your USB. It should, an electronic fusing there, nice. You should be able to actually limit that. But if you want the full power, of course, you know, the 15 watts, I don't think you might not be able to do that over the USB. But, and the USB port, there you go. The USB will only go to 5.5 watts total. So if you want higher power than that, you will have to use the auxiliary 5 volts there, up to a 15 absolute max. Well, it does say down here anything over 10 watts you risk thermal shutting down, but it's got lots of protections built in. Nice, you need that, especially in a school environment. Then we just turn on crazy stuff like a 3D spectrogram, for example. Like, that's nuts, right? We can bring that up, right? We can make that bigger. Look, it's just like seriously great stuff, right? This thing just, as I said, I could go for hours and hours and hours doing a video showing you every single feature of this thing. I can't possibly cover it all, and all the combinations of all the different things you can do. I just can't. And persistence. And then we've got eye diagrams, right? We've got histograms. We've got spectrograms. We've got FFTs, of course. You know, that's a given. And then you've got measurements, and then we've got login. And then we've got counter, is that just a frequency counter thing? Then we've got audio function. Stop it. I can't handle it. It's too many features. Okay, let's see if we can ramp our power supplies, shall we? In our waveform gen here, we can not only waveform 1, waveform 2, but we can actually use the wave gen to control the power supplies. Now, I believe you could do this in the Analog Discovery 2, although I haven't tried it, but you had to choose a certain mode. Now you can just do it freely in any mode you want. So let's choose the positive voltage rail here, okay? And bingo, we now have the ability to, I don't know why that didn't change. Oh, didn't change to an arrow. Didn't want to go full screen there. How do I get back? Like, you can have these on separate screens, which is really cool for multi-monitor setups, but like I can dock this back, but I don't know how to get back to like having the split screen. Hang on. Options, instrument windows, tabbed, separate, docking mode. There you go. Got it. You just go into settings there. Beauty. Bobby Dazzler, look at that. So what's our maximum frequency here for our power supply? 2.5 hertz. Yeah, that's not surprising, because when you want to characterize and simulate your power supplies ramping on, they typically ramp on in terms of milliseconds, hundreds of milliseconds, even microseconds. So yeah, so there you go, down to 1 microhertz, or you can just have DC. Anyway, so let's ramp up at a rate of 1 hertz, period 1 second, amplitude, okay, let's go from 0 to 1 volt, and 2.5 volts offset. Well, we don't want any offset, do we? And we don't want sinusoidal. What we want is a ramp up. There you go. So they've put that in there for us. Awesome. So we want it to ramp up. So now we want a single shot capture on our scope, our voltage ramp. Now I've got to tie the inputs so that we can use our channel 1 to measure our power supply. Yeah, here's where I would have preferred those silk screen on the top here. So our channel 1, the orange one, we want to connect through to our V plus there. And because this is a differential input, remember, we've got 1 minus as well. We should have to connect the grounds together as well, because this is not going to be a common ground scope, but it is not isolated. Don't think that this is isolated from the USB. I've done a video how not to blow up your oscilloscope. You still could come a gutter. Okay, there we go. We've got our differential across our power supply. Let's go. So there you go. We are pulsing at 1 hertz there, but it looks like we're going to need a load on that because it's not going all the way down to 0. So where our offset is 0, our amplitude's 1 volt, but yeah, our power supply is it is ramping. And watch what happens. I'm going to disconnect the ground there just to show you it's not a common ground. Bingo. Oops. Oops. I'm touching my finger on that, so we're getting our 50 hertz mains hum on there. Okay, so there you go. That's the differential input of this scope. But I won't go into the difference between single-ended and differential. There we go. I just put a random resistor across here, and you can see the perfect ramp up. And then we're going to discharge, because the discharge into the resistive load is the discharge of the capacitor. So that's going to be a capacitor discharge curve. But you can see, yeah, it ramps up. It ramps up perfectly. Isn't that great? And it's a half-second ramp up because it's a 1 hertz period. We can change that to 2.5 hertz, but there you go. Oh, silly me. I thought we could do fast ramp up. No, of course we can't. 2.5 hertz is the absolute maximum we can do. So it's only going to get slower, right? So we can ramp up over 10 seconds. Here it goes, over 10 seconds, right? So this is not really the tool to use if you want to like simulate like 50 microsecond turn on. You really need a professional tool for that. But still, it's handy to do ramp on. It'd be nice if it was a bit faster, but that's the limitations of, I don't know, the hardware in this thing. It can't go any quicker. But that's pretty cool, huh? We can actually ramp up our power supplies. That's got to be handy for certain applications. So that's a very useful feature, but unfortunately not as useful as it could be for like real proper simulation of ramping up of your fast power supplies, because you want to test your, most, as I said, milliseconds, hundreds of milliseconds ramp up kind of thing. This thing's not going to do that. It's only going to do that. This thing's only going to do 400 milliseconds absolute minimum ramp up time. So it's got to be faster than 400 milliseconds, unfortunately, but still, yeah, or we don't have to do ramp up. Like we can do a ramp down, so you can actually simulate your, let's try that, shall we? There's our ramp up and there's our ramp down. So if we actually stop that and we zoom in, how fast is that bad boy ramping up? That's not the software doing that. That's just the power supply telling it to go to another voltage and whoop, as fast as the loop of the internal power supply in this thing can actually go. I don't like the fact that when you zoom in on this thing, right, it gives you a vernier, but then it gives you like an odd scale at the bottom. You just get like a vernier scale at the bottom, like 0.906 seconds and 1.06 seconds. Like, it's just, can you like snap it to the nearest one or something? That'd be nice. Anyway, we can add, we can turn on cursors here, and if you want to add cursors, we can actually well, you've got to actually add a delta, actually, so we need to get rid of that, and it's not going to automatically give us 2, which is a little bit confusing, so we need another delta one, and boom, we need to snap that in there like that. And we can measure our ramp up time. But now they will track like that. So there you go, 7.5 milliseconds ramp on time. That's, you know, typical for a hardware power supply, which is what you get in here. Unfortunately, you can't control that. It's just as fast, it just ramps on as fast as it can. Yeah, if you want to turn on a lot of like stuff at once, you really do need a multi-monitor configuration, you know, to branch everything out. I'm not turning on a whole bunch of stuff. It's just, this is crazy the amount of stuff this can do. And check this out. This could be worth its weight in gold to a lot of people, right? I've got the power, once again, the power supply, we can do creative things with the power supply. We can generate, right? I'm just generating 3.3 volts, and here it is up here, right? It's measuring it live, 3.3 volts DC. But we can actually add noise on top of that power supply. So we can go 1 volt, right? Well, we're adding like random 1 volt noise at 2.5 hertz. Right? So that's just adding, right? Just random noise. That's just ridiculous, right? Or let's make it a bit better, right? Let's go up to 1 kilohertz. Look like one kilohertz is the maximum, but check it out. We've added 1 volt noise. I assume that's amplitude, that's peak to peak, is it? It doesn't actually tell you. You can actually set your peak. There you go. So you can actually set units here. All right, so you can set peak to peak. So if we wanted RMS, there we go. It adds a little RMS symbol. Oh, this is so amazing, right? So we can add 1 volt RMS, 1 kilohertz noise. Like, unfortunately, it doesn't have infinite capability. We can't like put on like 100 kilohertz switching noise or something like that, right? But we can add 1 kilohertz, right? Effectively 1 kilohertz switching noise here, and I like it to our 3.3 volt power supply. Are you kidding me? Like, that's just amazing. So if we want to say 50 millivolts RMS noise on there, there it is. We just added our 50 millivolts RMS noise, and we can do any of these functions, okay, up to a certain, you know, frequency limits and stuff like that. And we can even modulate the power supply based on what we read for our analog input. Oh, what? You can feed it back up its own clacker. This is just ridiculous. And then we can, once again, I haven't figured out these hardware filters or whatever, but all right, I've got my power supply on below me here. Unfortunately, we're not reading with the ADC at the moment, so I'm just going to short that out. So, oops, yep, there we go. There's our current limit. You can see that coming on red. So no wuckers, it's limiting that. It's not like shutting down our USB supply or anything. So let's do the same on 5 volts. Yep, we can just, short that, no problems. And it's all being powered from the USB, like this is just a USB 2 supply, no wuckers. And if I change it to plus minus 5 volts there, I like how it actually reads, the actual voltage back, and we'll see that actually drop like that. And the negative rail hasn't dropped, but it is limiting that as well. And you can see the USB current increased from 692, that's the supply of the Analog Discovery, and then, we don't have much to play with, and then it's gone up to 800 there for when I short the thing, so it doesn't have much current to play with. And it would have been, absolutely fantastic if it had like a proper power supply capability with current, like adjustable current limiting and stuff like that. But it looks like it doesn't actually, like you can limit like the hardware power limit, but it's not like, you can set up like a constant current supply or anything like that by the looks of it. And let's plug in an external 5 volt power supply. Auxiliary voltage. No, it's not there. Oh, I just plugged in an external 5 volt power supply and something popped up. Don't know what that was. Can I do that again? Hey, I've disconnected the 5 volt supply and it's still showing down below that there's 5 volt aux. Let me short out the power supply. 4.6 volts. That's interesting. Is that a bug? It's still showing auxiliary current. I am not plugging in any auxiliary supply voltage. Let me plug it back in now. 4.7. No, what's going on? Have I got it like, is it locked up in some state? Because it's not changing. Try turning it off and on again. I'm going to remove the USB power. Here we go. Okay, communication with the device failed. I think that's what it popped up with. Is that what it popped up with before? Okay. Let's plug it back in. Okay, I'm reconnected. It's redone its thing. Okay, now it's down to 0 volts, aux voltage. Now let me plug in the aux supply again, 4.7 volts. Okay, now we're good. So again, if I short out that supply rail, it's USB current, but it's only drawing 29 milliamps from the aux. So let's say set it to 5 watts or something. There we go, 1.2 amps. Now from the USB is 1.2. So that, why? No, my USB port's not capable of 1.2. I think there's a bug there. I think I found a bug. Something's going on with the monitoring. I think I've discovered. Oh, and it's not okay. And I've got it, the load is no longer shorted, and it's still showing 2 red buttons down below. So it's still, but it's dropped down to 680 milliamps. But it's still, the master enable is on, off, on. 680, right? There you go. It's not actually recovering automatically. 1 point, and none of that current's coming from the external aux, which there. No, it did for a second there. I'm physically dicking around with that. So is that there? Nah, I think I've got a dicky connection. Maybe I don't have the correct barrel jack. Yeah, what diameter pin have they used on that? I've tried 3 different 5-volt plug packs now, and they're all not the correct diameter. Yeah, so that's embarrassing. All the plug packs I can find here, 5-volt ones, are all 2.5 millimeter pin, and this thing is 2.1 millimeter pin. But yeah, you can see that when it's actually connected, all of the current, all of the output current comes from 1.2 amps there, is being supplied from the auxiliary device. Oh, now it's disconnected. Oh, because yeah. So there's an intermittent contact. So if you've got intermittent contact on your power supply, yeah, it's sort of the comms, the USB comms comes guts are a little bit. Don't know if that's like a small hardware issue or whether or not, but just use a reliable power supply. Don't be like idiot Dave. So what I'm doing is I'm shorting the input, and you'll notice that the persistence there is like 10 millivolts. So that's like, I'm not sure where it's getting that from. So, because if we stop it, right? The noise is not as high as what those peaks show there. So that's interesting. So like, surely it doesn't have like a peak detect mode. It's not that advanced. Anyway, we can add measurements here. So we can go channel 1, and then we've got horizontal, vertical, or custom. And then we can go over there, all our vertical ones. So AC, RMS. So that's what we want to measure our noise. I've done a video on AC, RMS. Hello, add. It's automatic. It looks like it's automatically added them all. Really? Okay. Yeah, there you go. Anyway, RMS, AC. Oh, it stopped. RMS AC noise is 600 microvolts there at this particular time base, and sample rate. Go down, it drops a bit. There you go. Yep, expand the time base. It's dropping. Yeah, because we've got limit. This is going to be determined by your memory depth as well, because I've done a video on oscilloscope noise and stuff like that. I'll have to link those in. But yeah, 250 microvolts. So, up to 1.5 millivolts AC RMS of noise there, right at the top end. And I'm not hugely interested in like measuring crosstalk and its performance and all that. Leave it in the comments down below if you want me to do actual, proper performance measurements on this thing. But yeah, I'm just having a play with it today just to see what's what. And the auto set seems to work on this thing. No worries whatsoever. And there we go. Yeah. Well, I don't want to trigger on either. There you go. So let's have a play. And also there's like record functions, and there's all sorts of there's just tons of stuff on here. I mean, just look at this. We can do an XYZ plot. Yeah, look, we can rotate this around, right? So we can get an isometric view of that. Right, check this out. I've got an XYZ plot, and you can choose what your X, Y, and Z axes are. And then you've got your isometric view. Okay, I should actually, can I expand that to full screen? Yeah, I can, right? And then, then we can move your isometric view around. It's just amazing what we can actually do with that, right? And then we've got an XY as well, right? So you can do all your regular lithogous patterns and all that sort of stuff. So that's not going to look very good at the moment, but that is just terrific. Like, I'm not even using like a proper example to show you here, right? I'm just dicking around. So I can get an FFT there on channel 2, and there you go. That's the FFT on channel 2 there. It's going to give you your usual like FFT capabilities. Once again, like I'm not going to check go into performance stuff and things like that. So there's our 100 kilohertz sine wave there. That's the orange channel 1, and then the second one, the blue one, is channel 2 there. So, you know, we've got all our usual FFT stuff plus all this extra capability, and we can put all these, dock them on different screens. Imagine if you had like 5 or 6 screens, and then, as I said, like we've got a spectrogram as well. Can we go full screen on that? Right, there's our spectrogram. Once again, not the best example, right? But the fact that you can actually do this stuff is just incredible. And there's a 3D spectrogram, right? Come on, seriously, this is fantastic, right? So this is like really, like, unfortunately it doesn't work in the RF domain, right? This is low frequency stuff, but it gives students the idea, and if you're learning this sort of stuff, and you can get to learn what an eye diagram is and a spectrogram and, you know, all sorts of stuff. You can learn all this stuff, and you can change all the axes to be anything you want, and it's just like, come on, this is just an incredible learning tool. If this is not the de facto standard in schools, I don't know what is. Right, so what that's basically showing is a frequency, right? This is the spectrum analyzer, right? The x-axis is frequency there, and that's showing our 100 kilohertz peak there. And it's basically just giving us all that information in 3D over time. Of course, that's just for a single sine wave. We can go to that more complex waveform we had on channel 2, and look at that. It's beautiful. And then you can change all the axes, and you can change all the scaling, and you can do whatever. Like, and I haven't even looked at like the login, like, and just a voltmeter, right? We can just get, like, you can just use it as a voltmeter. It's not terrific because you don't have like proper multimeter capability, but you know, it's there, right? And then we've got the logger. Haven't even looked at the logic analyzer. Haven't looked at the pattern generator. Haven't looked at the static IO, where you can like just, yeah, here we go. We can just turn on outputs, can we? I don't know, haven't enabled it, whatever. Sure, it all works fine. And then you get amazing stuff like a network analyzer, impedance analyzers, just like that, the Bode 100 that I've got. I've done videos on that. And then a curve tracer. It's probably only going to go up to the supply of the, you know, can't test at high voltages. Component curve tracing, right? So that you can learn how like curve tracers work. And protocol decoders. And then you can script all this. Like, anyway, serious hats off to Digilent, who's NI now, but yeah, hats off to the team who actually develop not just the hardware, but, you know, because the hardware's just the hardware. I'm not going to say it's not great, but, you know, it's just, right, it's just hardware. It's an FPGA with some analog to digital. All the magic is in the software. This is what you're paying for, right? This is just not, and I haven't even, like, seriously, I barely scratched the surface of what this thing can do. Anyway, this video is more than long enough. It's not a proper review. It's just a first, you know, playing around with first impressions. Let me know your thoughts and comments down below. But yeah, like, seriously, this is just an incredible bit of kit. You should, I think, you know, especially if you're on the road or something like that, and you want like an all-in-one, you want to, you know, just get, like, use a scope out in the field. And I'm sure you can buy, and also people have developed, I'm sure, open source like interfaces for this thing, front ends. I've just got this one, which is a basic BNC, and this is this single ends your input too if you get this board, so it converts your differential into a single-ended input and output. Then you can probably get ones with like, you know, screw terminal power supply interfaces and all sorts of stuff. And it's just, it's an amazing bit of kit. And for like under $300 US, I know it does sound expensive for what you get, but the software capabilities are just insane in this thing. And it's worth every cent. But of course, as I said, this is not a replacement for a desktop oscilloscope, right? You still need your desktop oscilloscope with your proper front end and your high bandwidth and yada yada, right? Your huge memory depth and everything else, right? This has got relatively small memory depth because it doesn't sample in real time. It captures it in the FPGA buffer and then dumps it. So you know, there's lots of blind time and everything, right? It's not a real oscilloscope, but the software and the capabilities more than make up for this. So yes, you should have a benchtop scope and one of these. It's just amazing. Anyway, hope you found that useful. If you did, give it a big thumbs up. As always, discuss down below and over on the EEVblog forum. Catch you next time.